Hello, everybody. It's Mrs. Pound. We are studying Chapter 14 on solutions from BJU Chemistry's 5th edition. Today, we're going to finish out the section 14.2 on measures of concentration. Previously, we looked at mass fraction, volume fraction, and molality. Our objectives today are to compare the different ways to report the concentration of solutions and solve concentration problems. So, amount concentration, we're just going to really focus on one type of concentration measurement today, and this compares the moles of solute with the volume of the solution. This is also known as molar concentration or molarity, and you will probably more commonly hear me refer to it as molarity when I'm talking about things in the classroom, about different solutions. And it is most commonly used in chemistry. So this is the most common type of solution a chemist will usually work with. So the equation is molarity equals moles of solute over liters of solution. This equation is found on the back page of your reference tables. So a question you might be asked using this equation is, what is the amount concentration of a solution that contains 3.40 moles of solute and 245 milliliters of solution? So we have molarity. We're looking for, I put molarity here because remember, amount concentration is the same as molarity. The number of moles is 3.40 moles, and I had to convert 245 milliliters to liters. So it's 0.245 liters. Just divide milliliters by 1,000. So our equation, molarity equals moles of solute over liters of solution. I plug in my 3.40 moles over 0.245 liters and get 13.9 moles per liter, or 13.9 capital M. So the label for molarity is commonly a capital M. Remember, for molality, it was a lowercase m. So you have to keep those two separate. Molarity, capital M, molality, little m. Think chemists use molarity more, so that gets the capital. They think it's more important. You have a 0.615 liters of a 0.50 molar hydrochloric acid solution. How many moles of HCl does this solution contain? So you have your molarity, 0.50 moles per liter. You have your volume, 0.615 liters. We're looking for moles. So we plug those values into our equation. Molarity equals moles of solute over liters of solution. We have 0.50 moles per liter equals moles of solute over 0.615 liters. So we have that here. So to solve, we must multiply both sides by the 0.615 liters. So I rearrange that. Liters cancel out. And when we do that, we multiply 0.50 times 0.615, we get 0.31 moles. Another kind of problem we can solve is, what volume of solution will produce a 3.75 molar sodium hydroxide solution using 34.5.2 grams of sodium hydroxide? So the first thing we have to do is we need to convert the grams of sodium hydroxide to moles using the molar mass. So this is the molar mass here. Divide that into the number of grams, and I get 0.880 moles of sodium hydroxide. So now we have this information. The molarity is 3.75 moles. The number of moles are 0.880 moles, and we're looking for the volume. So we just use our equation, molarity equals moles of solute over liters of solution, and we get 3.75 moles per liter over here equals 0.880 moles over the volume. Now, I don't leave it as the capital M here because I want to be able to cancel out my units to make sure I'm doing the right thing. So We have this problem here that we just plugged into. We multiply both sides by V, so it moves the V over here, but then we have to get the V by itself, so we divide both sides by the 3.75 moles per liter, and it becomes this problem here. Our moles cancel out, so we get 0.235 liters. And because it's 1 over a liter, the liter actually flips up to the top too. So another thing we can do is we can dilute solutions, and we have an equation for that. That equation is MAVA equals MBVB. This is also found in the back of your reference tables. It talks about acids and bases, but it works the same way. It's for titration, but this works exactly the same way. So we're going to understand this as the molarity of substance A is MA, VA is the volume of substance A, MB is the molarity of substance B, and VB is the molarity of substance B. So an example would be you need 565 milliliters of 1.54 molar hydrochloric acid. In the stock room, you have a stock solution of 12 molar hydrochloric acid. What volumes of stock solution and water should you mix to produce the required solution? I do this calculation all the time, guys. This is something I commonly do. So we have this information. Volume A is 565 milliliters. Molarity A is 154 molar. Molarity of B is 12 molar, and volume B is we don't know. So we have our equation, MAVA equals MBVB. I plug in my numbers, 565 milliliters times 1.54 molar equals 12 molar times volume B. Now, here I don't have to change it to moles per liter because these labels will cancel out when I rearrange my equation. Now the molar cancels out. And I get 565 milliliters times 1.54 molar divided by 12 molar. When I divide those numbers, I get 72.5 milliliters of stock solution must be combined with water to make a 565 milliliter solution. So what amount of water do I need? Well, 565 milliliters minus the 72.5 milliliters is 492.5 milliliters of water because the entire solution has to be a combination of those two volumes. We can't just add 72.5 to the 565 or it would be too much. So our objectives were to compare the different ways to report the concentration of solutions and solve concentration problems. So this concludes the section on measurements of concentration.